OK, this is me. I'm Tom Payne. Most of you have seen me talk before. Normally, I focus on Go trivia, but this is a very different talk. This is a very practical tools for the daily Go programmer today. Out of interest, who here has used the encoding JSON package to decode JSON? Most of you. Who's used encoding XML to read XML? Who enjoyed the experience? So, yeah, part of your daily job is often getting data in from elsewhere. And sorry, I just need to get my notes, I realize, which I've left down here. Using coding XML, encoding JSON to mark up your Go structs with the struct tags is a real pain. So today I'm going to focus on these two projects, go-jsonstruct and go-xmlstruct, which, as you can see from the descriptions, they generate Go structs from multiple inputs. So this very much comes from the practical use. So first look at JSON. So JSON in the wild often has no real defined schema. An example of this that I'm using in my day job is a format called GeoJSON. There is an overall, this is for geographic objects, like the outline of a country, or the line of a road, or the location of fountains in a city. It consists of a geometry, and then this fairly abstract properties field. And you might encounter this in other places. If any of you are using a document database, where there's often no structure. If you're using MongoDB, you have my sympathies. You might have an unstructured JSON field in a database. You might be talking to a JSON REST API with no well-defined schema. So often, JSON in the wild, there is no schema there. And it's up to you as an individual to either write annoying Go parsing code. That's painful. So wouldn't it be great if we could generate schemas for this automatically? And I'll make this a bit bigger. This is exactly what this code does. So I'll give you the demos first, and then we'll go into how it works. So, example JSON file. The cat command is alias to bat, for any of you using that. Very simple stuff. You've seen this many times before. We give it a JSON file, and it generates the Go struct for it. There are quite a few existing JSON to Go converters out there. Similar schema. Whoops, sorry, let's do that again. Cat example. Star.json. Now we have two JSON files, and they're kind of similar, but subtly different. They have slightly different schema. You can see user height is an int in one and a floating point in another, and favorite foods exist in one but not in the other. What go-jsonstruct does is, given multiple inputs, it generates the most specific Go struct that can represent all of the inputs. So you'll see, in this case, favorite foods, it's a slice of strings, it gets the emit empty, it works out the user height m is a float 64, it's done this sort of mangling of on the inputs, like favorite foods is in camel case, and user height m is snake case, and it's converted this to nice Go exported fields for you. It basically, it handles all of the awkwardness for you. In practice, what you'll see is, let's do a JQ dot. This is a real example from work. This is a GeoJSON file of air navigation obstacles in the Tyrol part of Austria. And these are things like antennas and cable cars and power lines that things might crash into. So this is GeoJSON. The thing we're probably most interested in here is the properties field. And you can see there's things like object ID, Stan, Talberg, all these sort of things. So I could go manually through this and try and work out what all these properties are and what types they require. There are multiple features here with each Each feature has got its own properties. But with go-jsonstruct, I can just give it the whole input file, and it generates the overall struct for this. We have the CRS's coordinate reference system for those GIS geeks, and then for each feature, we see we've got each property, its go type, pointers for things that might be present or not, and nicely converted from the JSON, from the not particularly nice property field in the original JSON object. And that's it. It's one command. And you get your go struct. Let's have a quick look under the hood at how this actually works. Just checking my notes here. Yeah. So I'll stick up some code. And yes, go-jsonstruct. OK, so go-jsonstruct has 2 phases to it, which is probably pretty much what you'd do if you were trying to do this, following the same process manually. The first thing is it explores the JSON structure that you provide it, and it recurses into every nested object. It iterates over every single array. It looks at every single project property and object value, and it gathers statistics on what types it actually observes there. So this is in value.go, and I will, here is the key point. So we have a type called a value, which describes an actual value that we observe in JSON. And here are the statistics. They're simple counts. Observations is the total number of observations that we've seen this, so we can work out if something is always present. If something is always an integer, for example, the number of ints will equal the number of observations. If it's only occasionally there, then the number of observations will be greater than the number of ints. And if it's a number that's sometimes an int and sometimes a float, we'll see both of those counters increased. So for simple types, this is quite... remember that encoding JSON will only give you a map string any for an object, for example. For simple types, it's pretty straightforward. We increment the number. We also check for 0 values to know, so we can work out if we need to use omit empty. For arrays, there's 2 things we have to do. This first case at line 51, we remark that we've got an array. We also inspect the elements of the array. So we can actually say, this is an array of strings, or this is an array of ints, or this is an array of unstructured stuff. So, and similarly for objects, it's the same, which is this map string any. We look at, we don't count the number of objects, and then we recurse in. We look at all the properties. We can tell if we have a map string int here, for example, or a map, and we also recurse in to get nested structures. That's the observation phase. The generation phase, you'd probably write yourself. This is this go-type function. For structural reasons, we pass in the number of observations we have, and we count the number of distinct types that we observe here. And then, based on that, this is a horribly messy, but I don't know how to make it neater. Based on these conditions, we work out what the most specific go type is. And this returns a string which represents that particular go type. Probably an usual example here is this one. If we've only seen floats and we have more than one of them, indicating there's not a null there, the go type is float64, and this Boolean condition is whether we should use omit empty or not. This gets a little bit hairy as we go in, but the principles, I think, are reasonably straightforward. We have lots of options for whether we should how we should handle nulls and empty structs and such like. This is all combined together in a top-level generator object, struct, I should say, which is constructed. Let me do this on this one. Sorry, I should prepare this one. Oh, no internet. OK, we'll have to skip that then. Yeah. Oh, that's because I'm on Google Earth. That's why it's not working. Sorry, package.go.gov. I'm terrible at typing when people are watching. Sorry. At the top level, you have a generator which ties all this stuff together. You create it with a bunch of functional options. You can see a list there that's pretty configurable. You feed it. You feed it values by basically saying observe this, observe that, and then you finally call the Go code function to actually get the Go source code out. So that's go-jsonstruct. Where it starts to get more interesting is, there's one other thing I want to show you actually, which is this conversion of names. And we all know Go is fairly opinionated on how names need to look. They need to begin with a capital letter. We like uppercase, camel case. We don't necessarily get that with our input. You can, there is some code in there to try and work out what a suitable Go name for a variable is. It will do things like try to split it based on a kebab case or lower snake case, split it into components, work out if some of those components are common abbreviations. This is probably easiest look with the output of in the tests, and you can see it's converting JSON IDs into reasonable Go IDs. Interestingly, there are some properties which you cannot decode in Go because Go uses these struct tags, which have a certain format. Let me find an example. Do I have something? I should have prepared this bit. Sorry. So a struct tag will look, for example, like this. If the property name includes a double quote or a space, then Go is unable to parse it, and this will flag those cases. That's pretty much a corner struct. So that's go-jsonstruct. One command line tool to produce your go-jsonstructs. Go-xmlstruct, same problem, XML this time. So XML in the wild claims to be a structured format. You'll often see XML schema definition, XSDs, for example. But these tend to be very complex in practice. I'll have a look in a moment. And XML itself is just, it's just a disaster, but it's full of ambiguities. For example, there's no canonical way to represent a map in XML. I'll give an example in a sec. There's a question to use an attribute or a nested element. All of these decisions fall onto the person creating the XML schema or writing the XML document. These things are not consistent they're consistent within an individual schema, but they're not consistent across XML as a whole. For example, if you want to have a map from strings to ints, do you have a series of elements with with key and value attributes, or do you have a series of pairs with key and value sub-elements, or some combination of these? It's a disaster. There's no canonical awareness there. That said, these XML schema definitions do exist. XML in the wild can be pretty horrific. Here's something that I've sadly had to deal with. This is the same air navigation obstacle data. Well, actually, it's for different countries. This is for Austria and Germany. Basic air navigation companies equivalent of SkyGuide in Switzerland provide this data. This is what I think this is the Austrian stuff looks like. This contains pretty much the same data as that GeoJSON we were looking at earlier. The level of nesting is large. We're not even at the start of the obstacles here. This continues. Anyone who wants to convert this into a go-JSON-struct? You psychos. So this is pretty horrific. We are lucky. There is an XML, an XSD file, and in past I have generated Go code from XSD definitions. They provide it. Find.name, star.xsd. There are only 74 XSD files that you have to process. And in fact, it's only 35,000 lines of XSD. And these XML files themselves are of the order of tens of megabytes of XML. I personally, this is what prompted me to write go-xmlstruct. I did not want to untangle these things. So along comes go-xmlstruct. Give it your XML file, in this case, a 34 megabyte XML file, and out comes the same thing. What it's done here, this is more sophisticated than the JSON one. It's coping with all the nesting. It's working out when things are attributes. For example, the ID is an attribute, for example, whereas geoid undulation, which is the difference between, roughly speaking, difference between sea level and the height of the WGS84 ellipsoid. This is a nested string, where things contain actual character data. Let's use the car data markup there. All this completely automatically generated from the input XML document. So when you decode using encoding XML into the structure, you get fully type-safe access to your XML document. You can, of course, give it multiple documents. This is not particularly interesting, but I'll just show it anyway. I just feed it in 50 megabytes of XML, and now we've got the union of all these examples. What's useful here is if you want it just quick and dirty, and you just want to decode the XML file or the JSON file that you have, you just feed it into this tool, and you get a structure out you can use. If you want to be a bit more rigorous, what you can do, if your XML thing has a test conformance suite or a bunch of example documents, you can just throw all the example documents that you've got at it, and you get a real-life representation of the actual data, the structure of the data that you're seeing in real life. This, however, is still not fantastically nice to read. We've got a whole bunch of nested struct, and so these struct, and this is the name of a field that's got this elevated point struct within it, and the tag at the end. You can't do this with the command line tool, but like go-JSON-struct, go-xmlstruct comes with a Go API. It's written first as a Go module that you can import and then tune all your parameters for, and secondly, as a Go a command line tool written in Go, which is a thin wrapper around this. And when you're writing useful tools, I strongly encourage you to follow this practice of write a package and then write a thin CLI wrapper around it. And that will allow people to make much greater use of your code. Examples of this from the standard library is that the archive tar standard package is equivalent to the tar command. Archive zip is zip. Similarly for, what are their examples? There are definitely other examples, but I forgot them. But yeah, so write your stuff as CLIs. And what we can do with this is once we have, we'll just find now, look at that in a sec, this is now XML struct. We'll look at the examples. So this AIXM data, similarly to the go-JSON struct stuff, we create a generator with a whole bunch of functional options here. Export renames, we basically both, it turns out in this particular schema, we both have lowercase note, N-O-T-E tags, and uppercase N-O-T-E tags, which conflict. They end up with the same exported thing, so we need to disambiguate those. So we can override, rename things individually. Unit of measurement is an abbreviation, non-standard abbreviation, which is specific to this. This named types thing is going to look really nice in a sec. I'll show you that, the output in a sec. Package name, raw token slightly speeds up the parsing by using it. What this allows us to do is from that horrific XML that you saw, we actually end up generating this, where we have a top-level type for every single type of element that we observe in the input. And this is now actually pretty usable generated Go structs. We can't do this quite so easily with JSON, because JSON, we generally have anonymous objects as maps, whereas in XML, everything has a name, and we can use that name to give names to our types. Another nice example of this is, this is the first thing I ran at. This is our example input XML. This is pretty much standard XML, but it's got these horrible 80s or 90s style, everything uppercase, inconsistent abbreviation. I don't know if these had to fit into Windows 8.3 file names or whatever. But by configuring our generator with these renames and the name types, we get out what is nice human-readable Go. Here is a very minor detail. Here, the order of types that we produce matches the order in which we observe things in the input file. So it's even readable as a human. That we start with a high-level play, and the play has a front matter and a list of dramatis personae, and so on and so on. So this is another option that we can set. So how does this work? It's pretty much the same approach as, a final thing I should say here, to generate these things. So now I have a actual generator code that runs. I would normally use a go generate script, a go generate line, which runs my Go code to generate my final struct from the input files I give it. Under the hood, it's similar principles to go-jsonstruct. Check my notes. So this is our observe function. We are, once again, just calculating, gathering statistics on the sort of types or values that we observe. In XML, it's much simpler because we don't have arrays and objects. We only have pretty simple types. The values we can observe can either be attribute values or the character data contents of elements. Similarly, just like you saw with go-jsonstruct, there's a go type function which counts the number of distinct types. This probably looks quite familiar, and returns the simplest go type that represents all that we've seen. This is then combined together. Things start to get a lot hairier here. When we observe an element in an XML file, we have to observe all of its values, all of its attributes indexed by the attribute name, the contents of the character data within the XML code, all of its child elements, and we also record its order in which children are optional or repeated. So a simple one to start with probably is observe attributes. We have an opportunity to rename here. If the name is 0, then we ignore it. Otherwise, for each attribute, we observe it. This updates our stats on that particular attribute. We work out if attributes appear more than once. It's a possibility. They can be repeated. Or if they're optional, and sometimes we see them sometimes, but not others. It gets really messy when you look into the observing child elements. But this is both recursing over attribute values and recursing into the child elements of this particular element. The net result of this is a big tree structure we're marked up with the stats, and then we call the generate, the go type function on the values to find out what the actual generated Go code, or what the simplest type is. All this is tied together. This is the top level main of the command line interface that wraps all of this. We have obviously a bunch of command line flags you can set. We pass the flags. We create our generator with the values or the configuration chosen by the user. And then we observe either standard input or a list of files, and we call generate and write the output file. So here, all of the functionality is in a package that we can use, but we also have a convenient CLI around it. Oops. No, one. An interesting, just a random observation from XML, from the XML package in Go. No, that's at the end. I found this a very interesting observation. I'll give you a moment to read it. So XML doesn't map onto data structures. We are hacking this, basically, and it's just the nature of XML that it's just not very good. Yeah, you can have that. But it's worth bearing in mind, if you have a choice, use JSON instead. So that's it, the summary here. So the two tools on my GitHub page, go-jsonstruct, go-xmlstruct. You can give them multiple input files. That's the real key differentiator compared to existing tools, where they only take a single input. You can feed them whatever documents you have, a single document for a quick hack, entire test suite, a whole entire conformance suite, and it does most of the awkwardness for you. No more renaming, no more working out what's nested, what's repeated, whatever. It does it for you. It's fully customizable. We saw a lot of those functional options. It has repeatable output. This is an interesting, the go-jsonstruct, actually first, at one company I worked at, they had effectively a document database which was populated with a Python script. And the problem with Python, well, Python's a fantastic language, but it's dynamically typed, and it's very easy to end up with a mix of types in your output. And there was a big data processing pipeline that produced effectively JSON at the end. By running this tool repeatedly and including it as part of the continuous integration process, I could detect when the Python code introduced by accident a new type. What was previously a bool now became suddenly a bool or an int, for example. The output is repeatable. Things are sorted, things map to the same structure, the same exported names each time. So you can actually run a diff against what you've checked, the generated Go code that you've checked in, and the generated Go code from the latest output you have. Command line interface for quick and dirty use, and a Go API for advanced use. Combine it with Go generate, and you have zero effort ingest of JSON and XML data in Go. Thank you very much.